All right, well, welcome everybody to our CT sessions. I'd like to thank Ken Coleman, who organized this session but is unable to be with us here today, so he was unable to make the meeting. But he did a great job putting together a nice selection of speakers for us. So we'll go ahead and get underway. John says he needs every minute, so without any further ado, let me introduce John Boone from UC Davis, and he's going to be discussing image quality or updates to image quality and dosimetry metrics for CT. John, thank you.
Good morning, and thank you to the organizers for having me along here. And so today we'll talk about some of the updates in image quality and dose metrics that have been ongoing in various circles in computed tomography. You can see I list my day job affiliation here at UC Davis. But here today with you, I also represent the AAPM Science Council, and I've been a member of several of the task groups that we'll be discussing today. I also chair the ICRU Committee on CT, and that's pertinent to some of the things I'll be discussing this morning as well. So here's an outline of what we'll be talking about, and I'll just point out to you without going through it in detail that this essentially aligns with many of the activities that have been ongoing in the AAPM over the last really about 4 or 5 years now, and so we'll sort of go through these in some kind of a rational order. Before that, I am required by my employer to share with you my corporate disclosures there. So by way of introduction, and I suppose the reason why we're all here today is CT is a different beast than it was 10 years ago, and this just shows some of the images that we've all become used to looking at, and the reality is that CT has become a very important diagnostic tool across virtually all stripes of medicine, and as a result of that, physicians have ordered this examination with increasing frequency over the last 30 years. As you see this data that's been compiled by Brenner, and you can see the blue line that I did an analysis at my institution, and I'll just suggest to you that what we're seeing here is two real inflections in this growth curve that happen to correspond to major technological advances in CT over the years. The introduction of helical CT led to a pronounced upward trend, and then with multi-slice, which led to even shorter scan times, had another pronounced upward slice. At my own institution, this nick in the trend line corresponds to the point in time where we installed 2 GE CT scanners in the emergency department. We're the third busiest ER in the U.S., and of course, if you build it, they will come in that case, and they did. So given the technological advances in CT that you see listed here, of course there are many more, the reality is that the dosimetry standards that we use today are really called back 15 or more years ago, and that's what we're here to talk about today. And so advances in TG 111, 200, and 204 is things that I will be talking about today. So before we get started with the new advances, I thought it would be only correct to spend a couple slides talking about where we are right now, and this is essentially codified by the IEC, FDA, and other probably state laws as well. And so CTDI 100 dose metrics and its various derivatives. And so most of you are clinical medical physicists, as am I, a part of the time, and so we all do this. We take these 32 and 16 centimeter PMMA, polymethyl methacrylate phantoms, and we insert a 100 millimeter probe and make an exposure both at the periphery and at the center. And we take these measurements and we combine them in a 1/3, 2/3 rule, which leads to the weighted CTDI sub W, with the advent of helical CT, which we all know that dose goes as 1 over the pitch, and so the CTDI vol is this weighted CTDI divided by the pitch, as you see there. And then we know that the scan length has an impact on essentially the risk associated with the scan. And so when we multiply CTDI vol times the scan length in centimeters, we get the dose length product, DLP, which is in the peculiar units of milligray centimeters. And the European Union, and now in America, we make use of this conversion factor, the so-called K factors, for various examinations that you see listed there, and we can convert DLP using this K factor to an estimate of effective dose in millisieverts. So the units of K are millisieverts per milligray centimeters. So that's where we stand today. This is what I taught my residents last week when I lectured to them, because that's sort of what's going on today. What are the limitations of this as we strive to have more accurate dose estimates in CT? Well, one of the largest issues is that the average patient isn't 32 centimeters in diameter. In California, I did a study, and it might be a little bit smaller than elsewhere because of a large Asian population in my community, but the average effective diameter was 28 centimeters compared to the 32 centimeters, which is really closer to a much larger individual because of the high density of PMMA relative to water or tissue. And so this phantom, the 32 centimeter body phantom, corresponds to a person with a 47-inch waistline. I'm a big guy, but this is a person much bigger than me. And so that's one of the limitations. And so let's move on and talk about some developments by way of hybridized or a harmonized image quality and CT dosimetry phantom. And so we're trying to address this very limitation, and that is that not only is this a little bit large, but it's also not very long. It's only 15 centimeters long. The chamber itself, as you know, is 10 centimeters long. Some work that myself and others have done over the years have demonstrated that the dose tails, and we'll see this plot again in a little bit, if this is the point where a very thin slice axial primary scan is, you can look at the dose tails all the way down to 1%. If you really want to capture 98% or so of the dose, you're going to need a much longer phantom, and you're going to need a much longer probe in principle, or a different method for capturing those tails using a smaller probe. All right, so the work of Task Group 200 is to come up with the proposed phantom, and this is it. So this is a 3-module phantom, a total length of 60 centimeters into 3 20-centimeter modules. Each one is 13.5 kilograms or 30 pounds, so together this is 90 pounds. It makes sense to split it up into 3 individual modules just so one can carry it around. We've designed it up. We've designed some packaging material so that when you have it on the table that you can keep it from the individual segments from rolling apart. There's alignment pegs and things like that. I'll just point out that it's 30 centimeters in diameter, and not 32, and it's made of polyethylene. It's not made out of polymethyl methacrylate. Polyethylene is a very close surrogate to adipose, so it's not water equivalent. That would be nice, but we're also striving to achieve a certain economy here. A water equivalent phantom that's solid, you know that solid water is exceedingly expensive to manufacture. This is an extruded material that's relatively inexpensive, and as the population becomes a little bit more obese, adipose is probably a better surrogate than water anyway. So this is a side view of the phantom, and I'll just point out that it has an MTF module. It has a complete homogeneous area for calculating the noise power spectrum, and then it has, of course, the holes that can accommodate point dosimeters at various diameters, center, edge, and an intermediate value as well. So I've had this phantom manufactured and at a machine shop, and you can see the 3 individual sections here. I'll just point out that we have a little cup in the center section, and we have some modules that we can insert in there to calculate the MTF, to measure and then calculate the MTF. And then section C is really just a homogeneous area for noise assessment. All right, so this is where it all began, and some of you in the room were around in this era when CT scanners were sort of had the same shape of the cars of the 70s, and the only output really was a sheet of film, and that was true for the radiologist, and it was true for the physicist as well. Before PACS, before DICOM, back in the 70s and 80s, the only way you were going to ever look at anything pertaining to image quality was printed out on these pieces of film. As a result, we have phantoms that have inserts that allow subjective eyeball-based assessment of both spatial resolution and contrast resolution, slice thickness, and other modules that you're all familiar with. But I'll say, even as we fast forward today, even the president of the AAPM, who's 2 offices down from me, you can take one of these, and now they are on the PACS system, but they're still qualitatively designed phantoms. They're not meant to measure a modern equivalent of, or a modern parameter associated with image quality, with spatial resolution in this case, which would be the MTF. So what we're proposing is, instead of using a phantom that really works in a clinic, I'll admit that, but we have a module that we can stick in, and that allows us to compute the oversampled line spread function, and Fourier transform of that gives you the MTF. And I'll just show you some of the results for one vendor's scanner. And so this is the in-plane, the XY plane, and you can see the effect of the various kernels. And I would claim that you can see, I mean, these are quantitative graphs, aren't they? And you can also see the effect of slice thickness. So back when in 20 years ago, we used to talk about the slice sensitivity profile, which is really the line spread function in the Z dimension. That made sense when it was 10 millimeters wide, but now that it's really 0.5 millimeters wide, it's the same dimension as the in-plane. And so why not just talk about spatial resolution in all 3 dimensions, and that's what we're proposing. And these are the MTF curves in the Z dimension, in the slice thickness dimension. And of course, as you go to thinner slices, your MTF improves, that we've all seen with these isotropic images. So that was spatial resolution. What about noise or contrast resolution? And you're all familiar with low contrast detail phantoms. I've always thought that these were very subjective. And so the idea here is that we have this module, and let me run through that with you. And so you would put this phantom on the scanner. You dial up a very high technique scan, and you image. And that high technique gives you a nice, high-quality reconstructed region for you to assess MTF, because MTF is best characterized at a high-dose scan. So you've made the dose measurement as you scan through that, and whatever it was, we know that we can adjust the MAS linearly down such that we can come up, so we can set a dose. And so we're going to set, let's just say 20 millimeters. You can set anything you want, but I'm throwing that number out today for you to think about, and at the center of the phantom. And then we rescan at whatever MAS is going to give us 20 milligray. We then remeasure it, and then now you reconstruct this module, and you have a bunch of images in which to evaluate noise at a preset dose level. And we can assess noise using the 2D NPS or the 3D NPS. I have my foot in the clinic and I have my foot in research, and so I'm being lobbied by various factions. This is easier to understand and easier to perform, but this is probably the more correct thing to do, because CT really is a three-dimensional imaging modality with 40 slice scanners, 64 slice scanners today. And so the idea is that you have the image, you place some region of interest, the 2D FT, after some normalization, you get the 2D noise power spectrum here. I'll just point out to you, if you're wondering what this donut is, the donut is the noise power spectrum integrated over 2 pi. The center of that right here, going along a line, is really the ramp filter that's, of course, part of the back projection regime. And then the roll-off at this end is the roll-off of the apodization filter that's always used in CT for noise management. And so we can convert this function by doing a 2 pi integration and come up with a 1D noise power spectra, which is easier to put in your reports and easier to sort of look at. And similar to the MTFs I showed earlier, these are the NPSs, the noise power spectra. And look at the power of this technique. As we change the MAS, as we go to low MAS, we have a very high noise, and as we increase the dose, we reduce the noise, as you would expect. So that's the effective technique. We can see the dramatic effect of the kernel here, which of course is important. And now that some scanners have 30 or 40 different kernels, we medical physicists are often asked to try to optimize that, and you're going to have a hard time doing that based upon a subjective radiologist looking at it. Oh, I like that one better than that one. I mean, you'll be chasing your tail on that type of a thing. So I'm a strong believer in this aspect. The other thing is, as we go to thinner and thinner slices, of course, at the same technique value, you're capturing fewer photons, and so you see the effect. The noise goes up as you go to a thinner slice. So this all makes sense with respect to the noise power spectrum. So as we move to a 3D noise power spectrum, it's really the same thing as what I just showed, except that you actually have another axis, and so this is a family of curves as a function of Z, and this is for a smooth filter, and you can see that this is for a bone-type filter on one manufacturer's scanner. So I'll just say, sort of in summary here, rather than looking at very subjective and qualitative phantoms that we've had for 30 or more years, the idea of using a noise power spectrum allows us to really objectively and more scientifically assess the noise on CT scanners as a function of the many parameters that are involved. So in summary, with respect to this aspect of my talk, in the old era, we had a complicated phantom that was expensive, eloquent in design, but the analysis was really just an eyeball analysis, owing of the era when these phantoms were developed. It was really some subjective analysis, and so the results were largely perfunctory. The new era uses a very basic, inexpensive phantom, really just extruded polyethylene. We use the modern mathematics of sophisticated image quality assessment, and the results then we claim are useful and quantitative. And I don't have the normal slide I show, and we're not just proposing the phantom, but we're also will provide the software for free. So we don't expect you all to be out there coding up Fourier transforms. This will be a package that, this is under AAPM and ICRU committees, and I fully intend to use my role in the AAPM to have this as a free download software from the AAPM website. So let's move on to talk about CT dose versus scan length. And this is really very much related to TG111, which was chaired by Bob Dixon and came out last year. Many of us were on this, not without its controversies. And so let's just sort of go through some of TG111 and what it teaches. And really what it teaches is to start with the beam profile, as I try to show you here. So this is the beam, just if you were to measure it. And we can look at axial scanning analytically, and you can see this comb of delta functions that's described here. And so the dose is really the sum of the doses of a series of axial scans. We can look at helical scanning, and this is a true integral, at least at the center of the phantom. It's not true at the edge. And it's a smoother distribution there, but they're largely comparable. And so what we come up with as a function of scan length, and so here's scan length, you see because of these low amplitude, long ranging scatter tails that exist along Z in CT, this primary was the same amplitude in all of these plots. The difference in the plots is the scan length. You can see here's a narrow scan and here's a wide scan. And look what's happening to the dose at the center. The dose at the center increases a lot, and it finally becomes sort of asymptotic. So in the next slide, I'm going to show you this as the x-axis, and this dose is the y-axis. And so this is dose as a function of scan length, and you can see for small scan lengths, you have lower values, and then you reach this so-called equilibrium dose somewhat asymptotically at some large scan length here, begging the question of how long should your phantom be, and we already talked about the phantom there. So the TG111 methodology for assessing this so-called rise to equilibrium curve goes something like this: is you put a point ion chamber, Dixon refers to it routinely as the farmer chamber, but it's really not an older farmer chamber, and the people who make the chambers ask me to quit calling it a farmer chamber. So you can do a small scan length and measure a value. And then you have to, if you've driven CT scanners, you have to, on a GE scanner, you have I's and S's, and you have to, and you know, you'd have to have a spreadsheet to do this because it's easily to get confused when the tech's breathing down your neck. But anyway, if you're able to do that, then you want the scan to be centered on the probe. You make that next measurement, and so on. And after some number of measurements, you actually then paint out this rise to equilibrium curve. Okay, so I'm going to extend this with some work that Bob and I have done more recently. And so I published this some 2 years ago, and I did a Monte Carlo study where we put dose at the center. So it was a sort of a delta function of dose, of primary radiation, a full 360-degree axial scan. And then we looked at the dose tails. I'll just point out that this is semi-log. This is a logarithmic axis, and this is a linear axis. And we looked at this trend as a function of position in the phantom composition, diameter of the phantom, and the energy, the kV of the X-ray beam. And a couple things become apparent, and this is where we put the primary, is that on the semi-log you can see the linear tails, and so indeed this is really a curve that can be well characterized by a bioexponential curve, as you see listed here. That's sort of key because if we can do just a little integration there, we can come up with the rise to equilibrium curve if you have the values of the dose spread functions that I showed you in the last slide. And Bob and I published this last year or whenever. The sort of amazing thing of this is we took that data and literally plotted it, and it overlaid the data that was published in the literature by Moore. This is not a fit using a free parameter. That's a direct overlay of the data, which has remarkable correspondence, as you can see. So moving forward, and I always thought that was a little bit of a tedious thing to have to scan for every point on the rise to equilibrium curve, and I've been sort of advocating real-time dose response curves lately, and I was working with a company in Canada to do this, but many other manufacturers have these sort of real-time curves, probes, I mean. And so the criteria really are that it has very fast output on the order of 1 to 5 kilohertz, which is not our MDH or Keithley meters today, although a Piranha or things like that, RTI makes some of these, and I know that MDH is working on it, and this is one that I got from a different manufacturer. And so the idea here, of course, one of the things about any CT probe is that it has to have isotropic response, and so we've characterized that, and it was very isotropic, well within 1% over 2 pi. And it has to be linear. This is not an air ionization chamber. And, of course, it's linear. It uses a photodiode. And so our modification to the TG111 methodology, and this will be in the ICRU document that's in draft now of the committee that I chair, as I mentioned earlier, is to do one scan and from stem to stern, all the way from one edge to the other, and you get this curve. And it turns out that all you have to do is integrate this, and you get the rise to equilibrium curve. So one measurement with a real-time probe gives you the data that you need to get this rise to equilibrium curve. Why do you need this? Why is this useful clinically? Why does it lead to more accurate dose estimation? And that is shown in this slide. So you have this correction factor. If you had an infinitely long scan, that correction factor would be unity, but most scans are not as long as infinity, And so if you have a scan of this length, you would use these various correction factors, and you could correct that patient's scan, because, scan length is something that's really listed in the dose header. In reality, scan length is not listed in the dose header, but DLP and CTDI vol is, and the ratio of those two numbers is the scan length in centimeters, as I'm sure you know, and so you can get that and make these corrections. All right, so let's talk then about TG204, and really the last speaker of this session, Dr. Diana Cody, will be talking about TG204 specifically. And this is hot off the press. I mean, we're going to put out TG204 as a report next week. It's been approved, and I just have to dust up a couple of final corrections, and it'll go out. But I wanted, rather than to steal her thunder about the details, I am going to describe something that we came across last week in sort of a realistic clinical example. And it was almost amazing that it turned out to pop up at this point in time, right when TG204, which I'm the co-chair of, came out. So as I've tried to emphasize, is the large phantom that we use for CTDI vol really gives a dose value that is an underestimate for smaller individuals. And so TG204 gives us guidance on how to make corrections for individuals that are either smaller, that could be small adults or pediatric patients, or are larger. So this is our situation. So we had a case that just came up in my clinic last week, and so we had a pediatric patient scanned on an outpatient Siemens scanner. CTDI vol was 4.78. This person had some issue with his chest and was going in for surgery. And so this scanner uses a 32 centimeter phantom for its CTDI vol measurement in the dose report, right? And so we can go in and make physical measurements of the patient's geometry here. Well, post-surgically, some NUS bars have been added to try to correct this defect. And that scan on a different scanner, because it was an inpatient now, both used AutoMA or CARE Dose 4 in the previous one, had a CTDI vol of 17.7. Well, the savvy mother of this child called our pediatric radiologist, is basically threatening lawsuit. Why are these numbers so disparate? And so Tony and I went in and we looked and we realized that one of the scanners was basing its CTDI vol value on the 32 centimeter phantom and the other one was on the 16 centimeter phantom. And so we used the correction factor. Diana may or may not show these tables, but these are part of TG204. And so before, the raw data, as listed by the machines, had a 3.7 difference in CTDI vol. After our corrections, we took this high value that was associated with the smaller phantom. The correction factor was 0.71, and we get this number. And vice versa for the other phantom. And you can see now the difference is really only 1.7, which is a lot better than 3.7. And that difference of 1.7 can easily be explained by the fact that the patient has some metal hardware, and in an AutoMA sense, of course, the scanner boosted the dose to penetrate these stainless steel external NUS rods. For what it's worth, the CTDI vol is not accurate here because these are external rods that are attenuating radiation prior to that beam actually entering the patient. Okay, and let me talk about CTI scanner output, and this is really one of the things that we've discussed with the ICRU committee over the last many years. And so I've sort of truncated this, and let's talk about characterizing the X-ray beam in this axis, which is the scan beam axis. And let me preface this section by saying when you measure fluoroscopy, when you measure radiography, when you measure mammography, you're really measuring the entrance beam to the patient. In fluoro, we use a phantom just to stimulate the automatic brightness control to get that number, but we often calculate MR per MAS or milligray per 100 MAS on a radiographic system and things like that. So generally speaking, you're looking at an external measurement on radiography, mammography, and fluoroscopy, whereas in CT, we have traditionally used a phantom and made internal measurements. And so the idea here is now that the CT beam is so wide, it's almost like a fluoro beam, a high MA fluoro beam that's circulating the patient, why not characterize the beam? When you put a phantom in a CT scanner, the story is a lot more about the phantom than it is about the scanner. I can assure you that, having done many Monte Carlo studies. The measurements that you get out are very much dependent upon the phantom that you put in, not so much, but to some extent related to the scanner itself as well. So what about this axis? Well, we have this real-time probe in our arsenal, if you believe what I said earlier this morning, and so why not put it on the end of the table and just have it translate through the beam as the scanner is rotating, and you essentially measure the in-air dose distribution at isocenter, and that's one characterization of the output of the scanner at a given technique factor, KV and MA. All right, what about the other dimension? And the other dimension, of course, is tainted by the fact that we have a bow tie filter in there, a beam shaping filter. And so thought about this for a while, and so if you put this same real-time probe not in the center, but rather at the periphery, and you scan, you're going to measure a trace that looks like this. And this trace, it turns out, and I wrote a paper about this, at the peak it happens to be when the probe is when the source is closest to the probe, and at this point it's when the probe is furthest away in the gantry from the probe. And so these two values actually correspond to the inverse square law. The rest of the curve corresponds to the inverse square law and the bow tie filter. And so because you can calculate those values, you can tease that out. The difference is all about the bow tie filter. You're essentially factoring out the inverse square law. And that allows you to characterize the beam shaping effects of the bow tie filter. And this is an example of that. Of course, it's symmetric, and so from 0 out to whatever angle, you can characterize that. There's a new paper that my student Sarah McKinney just published on measuring. This was a Monte Carlo study, but we've got validated this in real scanners more recently. So the idea is that we've made these two measurements of the orthogonal intensity of the X-ray beam, and you can put these together and really have something that looks like the output of the CT scanner in the absence of a phantom. Well, if you measure this at acceptance testing, and you'll probably measure phantom-based numbers at acceptance testing as well, if you go back after a year or 6 months, whatever your routine is, and you measure the same output from the source, do you really need a phantom? If the scanner is putting the same beam out, you would think that you don't really need the phantom in subsequent years. If you have a difference in the output, then it's time to break out the phantom again. But so, in summary, we strongly believe, we being the members of the committees that I have mentioned, and certainly the ICRU committee that I chair, is that CT scan and patient parameters really are useful not for calculating dose per se. CTDI vol is not a dose value. It is a metric that we measure, but we can use these data to facilitate Monte Carlo-based measurements, which is the basis of all modern X-ray dosimetry and gamma-ray dosimetry, not only for CT, but for fluoro and radiography and mammo as well. We all use Monte Carlo-based tables for these, and it's refreshing for those spirited individuals who get in and actually make the physical experiments to so you can validate the Monte Carlo, but ultimately there's too many parameters to do physical measurements, and we all rely upon Monte Carlo-based tables. And so we think that if you were to characterize the output of a CT scanner similar to a fluoroscopic or radiographic beam, that would be very useful, and it also gives you the type of data that you need for a Monte Carlo investigation. It gives you the bow tie filter and the beam shape in Z. So we've also talked about correction factors for scan length, and you know the scan length that's reported on the scanner, so you can easily make use of these correction factors. And we've also talked about correction factors, and Diana will talk about this in more detail in a few minutes, about correcting for patient size. It's a more dramatic correction here. And so with all these, we think that we can come up with a better dose estimate, and we're trying to use the word dose estimate as opposed to dose calculation to convey to all users of this information that it still remains an estimate, and it's not meant to be a plus or minus 5% dose calculation as our therapy colleagues are sort of required to do. And with that, thank you for your attention. So, remarkably, I actually have 5 minutes if you have any questions.
Can you go into, or do you want to tackle, from the practical point of view, are you really looking that every physicist is going to be carrying around a 60-pound phantom and bring that into every CT department?
90 pounds.
Absolutely not. It's a 90-pound phantom.
90-pound phantom. I mean, I'm sorry, I realize I'm the wimp, but I really have no desire to carry a 90-pound phantom around every CT scanner that we service. And I guess I'm just trying to figure out from practical, what are you really looking for versus acceptance test even, again, on every CT scanner that we cover, versus an annual evaluation?
Thank you for those realistic questions and comments. I think that the way that it will work is that you, of course, have the phantom on a cart, but that you, yeah, don't you have a cart? So you need a new truck with a lift, Melissa. So the idea is that this is probably more for those of us who are engaged in research, and it might be more realistic for acceptance testing only. And things that we have already talked about is if you measure this at acceptance testing, then could you get away with only an in-air measurement, no phantom? You'd appreciate that because the probe itself is light. Or why not use just the center module, which has the MTF, and you could also calculate noise power from that as well. So we're realistic and do these things ourselves. Cynthia, go ahead. So Cynthia is on the Phantom Committee, and are you too, Diana? So I always laugh at Cynthia and Diana because they go, we don't want to, because we're women and we're not as big as you, John. We don't want to go in and have to do that. And I go, yeah, that's fine, but I actually lift the Phantom. They have staff that go around and do that since they run large institutions. Any other questions? Sir.
In your committee, with this, discussed with somewhere else, moving towards refining our dose estimates, where are we as an organization working to put meaning to those in their use and evaluating whether clinical procedures should be done?
Well, that's an excellent question. It's much harder to answer. I think that we are to a point where we can actually assess the dose to the patient within some greater degree of accuracy. Probably, we're sort of talking about 20%, but the reality is it's probably, if you do everything right, it's closer to 10%. And so what then do you do with those numbers? Well, the user community, both radiologists, referring physicians, and patients parents are becoming more savvy with that. We have heated discussions about the use of effective dose, the K factors, because effective dose was never really meant to characterize a patient's dose. It was meant to be a generic patient's dose because it's based upon risk factors from a whole different group of people than that patient on the table. So if you really wanted to come up with risk factors, then you would have to use the Beer 7 tables, 12D, or whatever it is, 12A, and come up with actually age-specific, gender-specific organ-specific based risk factors, and those are about as good as you're going to get in terms of conveying the risk. I was on NPR last Wednesday, and the person asked me, well, what about all this kind of stuff? And I was talking about millisieverts, and I saw his eyes roll, and so of course you always have to couch it in terms of a 3 millisievert annual background dose, or a lot of people use chest X-rays as a unit of dose, but I'm not a big believer in that.
I'm worried about the AMA's patient record tracking dose model that projects that you're going to show up at a hospital and someone's going to pull up your dose history within whatever accuracy it has, and then make a decision about whether another diagnostic procedure is appropriate based on the risk associated with that dose. And I don't see in that model who's addressing how we're going to approach that.
So that's a greater issue, and that will, the forces are in play now, and that will happen. And I was at a dose conference that had the title Towards the Submillisievert Examination that was put on with the NIH and FDA. Diana was there, and perhaps some of you as well. And they were talking about a dose report, and Jim Thrall, who's the chairman of radiology at MGH, he was advocating a order entry process so when a referring physician orders a scan, that it pops up and says, do you realize the patient had a CT scan last night and yesterday morning, and things like that. And those are probably good things. We, the radiology community, need to do the right things to keep the doses down. The issue of if you've already had 50 millisieverts, should you have another CT scan? Obviously, that depends on why that CT scan is ordered. And so we've heard a lot in the press and New York Times and all that about the risk of CT and other radiation procedures. But what we're trying to move to is a benefit-risk discussion, because if that patient needs that scan for surgical planning or to see if they have a broken whatever, obviously that probably will outweigh the associated risk. So it's a more complicated question that's not able to be answered in a few minutes here, but I think you know where it's all heading. I need to sequester the podium, I think, to Doug. Okay, one last. Yeah. So I think that where we're headed in this is that we're giving the tools to allow the medical physicist to compute dose as a function of diameter of the patient and scan length. And so I anticipate in 3 or fewer years that there will be tables where you know what the kV, CTDI vol, etc., and the diameter of the patient is and the scan length, and you look to that table and make a dose estimate right there. Right.
In America, it's getting bigger.
Right.
And so we're defining the image content of the quality of the image for diagnostic versus not dose. Should we be looking at a bigger size assessment and trying to define when the image starts to fall apart? How much more risk that patient's at, a given scan or a given time?
So there are a number of researchers around the U.S., and I'll just mention Ihsan Sami's group at Duke is doing a lot of. You talked about how can you evaluate image quality as a function of task and size of the patient. He's doing specifically task-dependent image quality assessments using the earlier work of Tapio, Vera, and Wagner and stuff. So doing all the right analytical stuff. And I anticipate, you're asking sort of a futuristic question, and I think that in the future we will have those answers as some of that research comes to fruition over time. All right, let me give it up the podium. Thank you.